The universe just handed us something that breaks every rule we thought we knew about how big a star can get. And I don't mean slightly breaks the rules, I mean shatters them completely. Because out there, roughly 19,000 light years away, hiding behind a wall of cosmic dust so thick that we couldn't even see it until 1990, sits a star so massive that if you swapped it out with our sun right now, it would swallow Mercury, Venus, Earth, Mars, and reach all the way out to Saturn. That's what we're talking about today. Stephenson 2-18, the largest known star ever discovered. And according to our own models of how stars work, it literally should not exist. Here's what most people get wrong about giant stars. They think bigger just means brighter, hotter, more of the same. But Stephenson 2-18 doesn't follow that playbook at all. It breaks the physics we use to describe how stars form, how big they can get, and how long they can live. And the deeper you go into the numbers, the stranger it gets. I've gone through every major study on this star, from the original 1990 infrared surveys to the most recent spectral analyses, and what I found genuinely surprised me. So here's what we're going to cover. How this star was hidden from us for decades, what its size actually means when you put it next to things you understand, why it burns so bright without actually being that hot, and why scientists are still arguing about whether some of these numbers are even real. Let's start with the second most mind-bending fact about this star, because this one sets the stage for everything else. Stephenson 2-18 wasn't discovered because someone looked up and spotted it. It was discovered because someone finally built a tool that could see through a wall. The star sits inside a region of the Milky Way called the Scutum constellation, right along the galactic plane, and that galactic plane is packed with enormous clouds of interstellar dust. Not like dust bunnies under your couch. We're talking about vast, light-absorbing curtains of gas and particles that stretch across thousands of light years. Visible light hits those clouds and gets completely absorbed, gone, like shining a flashlight into a black curtain. For most of human history, and honestly for most of modern astronomy, Stephenson 2-18 was completely invisible to us. Then, infrared astronomy changed everything. Infrared wavelengths are longer than visible light. They don't get absorbed by the dust the same way. They pass through. And in 1990, American astronomer Charles Bruce Stephenson was scanning deep sky infrared survey data when he spotted an open cluster of red supergiants hiding behind that curtain. That cluster got named after him, Stephenson 2. But here's the twist. The star we now call Stephenson 2-18 wasn't even considered a proper member of that cluster at first. It was sitting off to the side, too bright, slightly wrong motion compared to the other stars. Astronomers basically filed it under weird outlier and moved on. It took years to follow up studies, maser emission analysis, spectral readings, and a lot of scientific debate before anyone fully reckoned with what they were actually looking at. And what they were looking at was something that had no business existing. That's important, but if you don't understand what the size of the star actually means in human terms, the numbers are just going to bounce off your brain, so let's fix that. The radius of Stephenson 2-18 is estimated at 2,150 times the radius of our sun. Now I know what you're thinking. Bigger number, so what? Here's so what. Our sun's radius is about 696,000 kilometers. Multiply that by 2,150 and you get roughly 1.5 billion kilometers. That's the distance from the center of this star to its surface. Saturn orbits the sun at about 1.43 billion kilometers out. So if you placed Stephenson 2-18 where our sun is right now, you would be standing on the inside of this star. Earth would be deep inside its atmosphere. Mars too, Jupiter, and Saturn would be right at the edge of its photosphere, teetering on the surface of a star. Every single rocky planet in our solar system, gone, vaporized inside a star. But the volume comparison is where this really gets absurd, because volume scales with the cube of the radius, not linearly, cubically. So when the radius is 2,150 times larger, the volume isn't 2,150 times bigger. It's 2,150 cubed. That's roughly 10 billion times the volume of our sun. 10 billion suns worth of space filled by one star. Here's an analogy that might actually land. If you shrink Earth down to a single grain of sand, the sun becomes roughly the size of a golf ball. At that same scale, Stephenson 2-18 would be taller than the Empire State Building. One star, Empire State Building. One grain of sand is Earth. Let that sit for a second. But here's where it gets even stranger, and this is the part that surprises almost everyone. You would think a star this massive must be incredibly hot, burning white or blue, radiating intense heat from every surface. It's not. Stephenson 2-18 is a red supergiant, and red means cool. Its surface temperature is approximately 3,200 Kelvin. Our sun burns at 5,778 Kelvin. So our sun is actually nearly twice as hot at the surface as this impossibly large star. And yet, Stephenson 2-18 is estimated to be 440,000 times more luminous than our sun. How does a cooler star outshine our sun by nearly 500,000 times? Surface area. Think about a campfire versus a football field covered in warm coals. The campfire burns hotter at any single point, but the football field of coals is radiating heat from an incomprehensibly larger surface. The total energy coming off that field dwarfs the campfire, even though every individual coal is cooler than the flame. Stephenson 2-18 works the same way. It's not a raging inferno. It's an ocean of relatively cool stellar material so vast that the total energy pouring off its surface overwhelms almost everything else in the galaxy. That's a framework worth keeping. Size beats temperature when the size difference is this extreme. Now here's a fun way to feel the scale in your gut, because the numbers alone aren't enough. Light travels at 299,792 kilometers per second. It takes about 14.5 seconds for a photon to travel all the way around the equator of our sun. Around the equator of Stephenson 2-18, that same photon would need nearly 9 hours. 9 hours at the speed of light, just to go around once. And if you want to feel it even more directly, imagine boarding a commercial airplane. Cruising speed, about 900 kilometers per hour. A flight around the Earth takes roughly 45 hours. A flight around our sun at that speed would take about 6 months. A flight around the equator of Stephenson 2-18, approximately 1,200 years. You would board that plane in the year 825. You would land today, and you would have done 1 lap. That's the scale of what we're dealing with. Now here's the part that should genuinely keep astronomers up at night. Stephenson 2-18 is only about 14 to 20 million years old. Our sun is 4.6 billion years old and is roughly halfway through its life. Stephenson 2-18 is a cosmic infant by comparison, a teenager astronomically speaking, and it's already dying. Massive stars burn through their nuclear fuel at a ferocious rate. The more mass you have, the faster the fusion engine runs, the faster you burn out. It's like a bonfire versus a candle. The bonfire burns brighter, hotter, but it doesn't last nearly as long. Stephenson 2-18 is already nearing the end of its main stellar life cycle, and when it goes, it won't just fade out quietly. It's expected to undergo a core collapse supernova. The core implodes under its own gravity in a fraction of a second. The outer layers explode outward in one of the most violent events in the universe, and what gets left behind is almost certainly a black hole. A star this large, this luminous, this brief ends as a black hole. That's the life cycle. born enormous, burn fast, collapse into darkness. Therefore, this star isn't just a record holder. It's a window into the extreme edge of what stellar physics allows, or maybe what it doesn't allow. Because here's the part that the scientists are still arguing about. The theoretical upper limit for how large a red supergiant can get, based on our best models of stellar evolution, is around 1,500 solar radii. Stephenson 2-18 is estimated at 2,150. That's not a slight overage. That's 43% beyond what the models say is possible. Some researchers think the size estimate is inflated because of the methods used to calculate it. The temperature reading of 3,200 Kelvin itself considered suspect. It would actually place the star beyond what's called the Hayashi line, which is the theoretical boundary where a star can no longer maintain stable hydrostatic equilibrium. In plain terms, it would mean the star is structurally unstable in a way that physics says shouldn't be able to sustain itself. On top of that, we're not even completely sure how far away this star is. The distance estimate carries an uncertainty of more than 50%, and distance directly affects how we calculate size and luminosity. If the star is closer than we think, it might be smaller. If it's farther, it could be even more extreme. We also don't know for certain that it's actually a member of the Stephenson 2 cluster. Its radial velocity is off from the other cluster stars. Some papers classify it as a completely unrelated foreground object. Others argue the velocity difference can be explained by the star's own expanding gas envelope pushing outward. The honest answer is this: we found something extraordinary, and we're still figuring out exactly what it is. And that's not a weakness in the science. That's exactly what science looks like when it bumps into something genuinely new. If you're the kind of person who finds this stuff fascinating, drop a comment below. Tell me which number hit you hardest. Was it the Saturn orbit comparison? The 1,200-year plane ride? The fact that it shouldn't theoretically exist? I read every single one, and those comments genuinely help more people find videos like this one. And if you want to go deeper into the universe's most extreme objects, there's a video right here that covers the most violent stellar events ever recorded. Supernovae, magnetars, the works. It pairs perfectly with what we just covered. Subscribe if you haven't yet. We do this every week. New star, new mind-bending corner of the universe. New reason to feel small in the best possible way. Let's bring it home. We found a star that hides behind a cosmic dust wall, invisible to human eyes for most of history. A star so large its surface would swallow Saturn's orbit, 10 billion times the volume of our sun, shining 440,000 times brighter. Not because it's hot, because its surface area is incomprehensible, only 20 million years old and already dying, and built in a way that our best physics says shouldn't be possible. Stephenson 2-18 isn't just the biggest star ever discovered. It's a reminder that the universe doesn't check our models before it does something. It just does it. And somewhere out there, 19,000 light years away, behind a curtain of dust that blocked our view for centuries, this impossible star is slowly, quietly running out of time.